G'day there. Welcome to the third in our series on solar and battery training. Today we're going to be looking at system configurations, particularly for hybrids, solar and battery on grid, and understanding the difference between AC coupled and DC coupled. Let's get into it. Let's dive into the topic for today, starting with, as you do with almost every vocational training, health and safety issues. Workplace health and safety is specific to the activity you do. There isn't such a thing as a generic OH&S course. So in the world of solar and batteries, there will be some specific risk factors. And these particularly the factors around DC. With solar PV, you're often working at quite high DC voltages. So your typical grid tie systems, single phase, will be up around the sort of 400 or 500 volts DC. DC is inherently less safe than AC at similar voltage levels because of the propensity to cause internal burns. So you have to be very careful with DC. In fact, that's why there's licensing requirements. If you're working on systems over 120 volts DC, or 50 volts AC, you need to be a licensed electrician in New Zealand or Australia. And that's for good reason. Even at slightly less than 120 volts DC, there's still risks, particularly from burns or people with sensitive hearts. You can still damage internal tissue. At extra low voltage, now extra low voltage is starting to become a bit of a redundant term, the way our standards are moving towards the IEC definitions, but as it currently stands in ASN ZS3000, extra low voltage sounds perfectly safe. Actually, it just means less than 120 volts DC. Now, if you've got a battery system operating in that range, it will still have an enormous amount of current potential. And so it's not necessarily electrocution that's the risk, or electric shock, but it's burns and possibly fire. So short circuits in ELV systems are a major risk too. So that's why it's very important to use insulated tools when working on ELV battery systems. LV batteries, of course, now you've moved above 120 volts DC and you're required to have a lot more protection. Now, there's a new battery standard out that's come out recently. It's published last year. It's been enforced in Australia now, and it's kind of soft enforced in New Zealand. So it's still a little bit ambiguous in New Zealand how the new battery standard is applied, ASN ZS 5139. But what it does say is anything over 60 volts is deemed to be hazardous. So it's lowered that bar quite a lot. And for good reason, because in damp environments, even a 60 volt battery system can be potentially a shock hazard. Some battery systems have combustible gases being emitted under normal operation, particularly, for example, lead-acid batteries. When they charge, they'll evolve hydrogen and oxygen at the cathode and anode, and that makes a very explosive mixture. So it's a requirement to maintain ventilation. There are standards that cover those ventilation requirements. We've also got chemical hazards. In the case of a lead-acid battery, it's an acid. It's a relatively mild acid, but you don't want to get it in your eyes. But other chemistries may have more toxic materials as well. Some might emit gases which are poisonous to breathe in, for instance. So you need to consider those in the design of a system. And lastly, of course, there's fire hazards associated with some types of batteries. Some battery systems can go into thermal runaway under fault, and that's being considered quite a lot in our new battery standard. For example, it is possible with some chemistries, some types of lithium-ion batteries, and there are many types, that thermal runaway can lead to a fire. So, and possibly toxic gases. So all of those things have to be considered as part of your safe work method when working with battery storage systems. So how are we going, Rachel? We've got any burning questions you want me to answer?
Yes. I'd like to hear your answer to this one for everyone. Jeremy's got a question. If DC is more dangerous than AC, why can you work on up to 120 volts DC, but only 50 volts AC without being certified?
Yes, good question again. Now, there's different reasons that AC is dangerous and DC is dangerous. AC is more likely at relatively low AC voltages to create what's known as fibrillation, where the heart beats irregularly and will not return to a regular beat. It doesn't actually outright kill you, but because your heart doesn't pump properly, that means there's a very high chance you could die. So defibrillation is required. So this is at a relatively low AC voltage. With DC, though, it's not a regular heartbeat that's a problem, it's internal burns. Now, to get those internal burns, you do need to go to somewhat higher voltages. Now, like I said, Jeremy, we have lowered that in the new battery standard to just 60 volts. So I think we're reviewing the safety issues around DC more carefully and following the International Electric Tech Commission's definitions of risk factors. In fact, the IEC deemed DC in a wet environment is hazardous over 35 volts. Yes, there's different risk factors, and I guess the main one is internal burns from DC. You can't recover from that. If you've got a burn across muscle tissue, it's probably, like your heart, it's probably fatal. There's no defib. How are we going? Any more, Rachel?
Yeah, Avery asked a question. I was just going to get a bit of clarification on it first.
So it sounds like Avery wants to know what standard. So AS/NZS, so Australian and New Zealand standards are often joint standards. And in the case of all our PV and battery standards now are joint standards. So we have AS/NZS 5139, which is the battery standard. We have AS/NZS 4777 Part 1 and Part 2 for inverter systems and testing of them. And we have AS/NZS 5033 for PV arrays. Hopefully that's answered Avery's question. Okay, let's get back to my presentation. Thanks for that, Rachel. That was great. So moving forward on workplace and health and safety, just to summarize some of those points, use appropriate lifting and moving equipment. I'm speaking from experience here as an old-time installer. I've moved a lot of lead-acid batteries, and lead-acid, being lead, is extremely dense and heavy. Particularly the larger off-grid systems, you're often dealing with cells that weigh 60 to 100 kilos. And considering that they're so dense, they're rather small for their weight and difficult to manage. It's like lifting a 100-kilogram egg. If you drop it, it's all over. Not only is it all over for the battery, but probably your toes as well. So use appropriate equipment. Don't just risk it. Don't injure your back. Make sure you plan your means of moving stuff. Don't just turn up on the site and go, how are we going to get it off the back of the ute? You also need to ensure the structural integrity of the system that you're going to mount it on. There's a lot of point loading with some batteries, and if they're hung on the wall, consider that as well, and that's the safety of others. There may be hazardous good regulations under your jurisdiction about moving those batteries around the country or around the city or town. And the last point, I make this a lot, use insulated tools when you're working on live exposed terminals. Now, some battery systems can be turned off within the cell or within the battery pack, but many have live terminals exposed as soon as you take the caps off. For instance, these lead-acid batteries you can see in the picture here, once you take the caps off those terminals are live, and if you were to put a spanner across them, it would be a very big short circuit. Even at 2 volts, the current is extremely high. So we're going to move on now from occupational health and safety and look at system configurations. But Rachel did point out to me before we started the webinar today that there's an OH&S issue even in this picture, which is just a random picture out of my collection. There's someone using a stepper drill to drill a hole through some ducting, and that is probably the most dangerous tool in my shed. If you get your hands around that stepper drill, it'll take all the skin off your hand and a lot of flesh as well. So you really should be wearing proper hand protection, probably eye protection as well when using that piece of equipment. Thanks for pointing that out, Rachel. So on to system configurations. I'm going to start with hybrid. Now, if you're not familiar with the term, hybrid in Australia and New Zealand is used to describe on-grid systems that have battery storage and solar. So it's kind of like a hybrid between an off-grid system and an on-grid system, or it's a hybrid between solar and batteries, a bit of both. The confusion often is the way people describe these hybrid systems in the way that the energy is joined, the energy from the PV array, the energy from the battery, the energy from other AC sources. And what I want to do here is describe those in more detail with some nice diagrams. Rachel, how are we going for questions?
But one just popped up. I haven't had the chance to read it yet.
Okay, well, I'll leave you to filter those for me. So you'll hear terms, particularly if you go to trade shows and you're talking to salespeople who often aren't technical experts, they're really sales experts, and they'll use these terms as if they're a generic term. They'll say, oh, ours is an AC coupled solution, or ours is a DC coupled solution. Now, there's nothing wrong with doing that, but they haven't defined it clear enough. So what I want to do for you now is give some diagrams and examples of AC coupling and DC coupling, and the pros and cons of those different approaches and the subtle differences within those. Some of those, for instance, are you can have devices that have just a single port. Now, what do I mean by port? I'm using the language of our inverter standard 4777. We refer to inverter ports, and that would be things like the AC grid port, the communication port, the DC input ports, maybe an AC output port. These are all ports. There are some systems that have a single AC port that can change its nature from being grid following to standalone. And I'll give a diagram for that in a second. We also have some which have multiple ports. That means that they've got a dedicated grid port, a dedicated standalone port. There are DC-DC conversion devices that can be put between a PV array and an inverter, and there's this terminology, an AC battery. Now, a battery by definition is DC, but once you put it into a package, and within that package there is an inverter, think of Enphase, for instance, with their AC battery, or ACB for short, or Powerwall 2, which is an AC output device. People think of it as a battery, but actually it's got a 5 kilowatt inverter inside that pack. So they're sometimes referred to as an AC battery. So let's start with AC coupled systems. Now, AC coupling actually is relatively new, really only about 20 years old. It's the ability to couple the energy from one source to another through an AC network. And in the case of a PV system and a battery, we're talking about the energy flowing from the DC side of the PV to the DC side of the battery through an AC network. That's the word coupling. The pros of AC coupling are that it's very easy to retrofit to an existing system. For instance, you may have an existing solar system and the customer says, oh, look, I'd really love to have a battery. Do I have to buy a whole new inverter? Well, actually, it's possible to AC couple that. Now, let me just show you an example. We'll jump back and forth for a second here. There we go. There we go. So there's an example of an AC coupled system. I call it a retrofit. So in this case, the customer already has the solar inverter. So that solar inverter is a pre-existing system, and they are wanting to be able to trying to annotate something here. They're trying to find a way of adding battery storage. So a Powerwall, and I put a red box around it to indicate that's one piece of equipment. What we would call a BESS, a battery energy storage system, BESS, can be just coupled via the blue lines, which is AC, into the existing installation. Now, a critical part of that, though, is that energy meter with a little transmitter that I've shown there. It's not actually a transmitter in practice, it's a dedicated cable. And the purpose of that energy meter, it's not the utilities meter, it's the meter that comes with the AC coupled storage solution. It allows it to see the exchange of energy that's occurring at the point of connection with the grid. Now, Rachel, I see there's another question popped up. Is that one for me?
Yes, it sure is. Richard asks, at some stage, can you explain the term grid forming?
Okay, so Richard, thanks for that question. Grid forming is a terminology used in off-grid AC coupling where one inverter, the one with a battery connected to it, will form a stable grid. Basically, it's what runs the home or the installation. And so it's setting up a 50 hertz, or if you're in the 60 hertz world, 60 hertz stable frequency and voltage. And so it's powering the installation to which grid paralleling systems can connect. So you might have an AC solar inverter, which can synchronize with that grid forming inverter. I hope that explained that one. Now I'm just going to bring that diagram back up. Let's see how we go here.
David Lamb has noted on your diagram that the inverter is showing AC out of the DC input.
Oh, thanks, David. Well, let's just call that my favourite electrical engineer's comment. I'm not sure if you are, David, but it's about the units that, or not the units, the symbols that we use for drawing. The symbol for an inverter. So what David's referring to is this symbol here, which is a symbol for a inverter, a device that converts DC to AC. And the location of the connections to that symbol are irrelevant. So basically, you don't have to make sure that the DC lines connect to the DC side of the symbol. So let's just ignore that one. And if you doubt me, check AS3000 Appendix J. It explains that. So where I was going with this diagram, by the way, is trying to show the importance of this energy meter over here. Now, this energy meter is allowing the communication of the flow of energy. So is the energy flowing out of the installation? And it can see that because it's got its own current transformer and voltage reference. And so if this PV system down here is pumping out 5 kilowatts of power, so we're pumping out a nice 5 kilowatts, it's going in this direction, but the customer's loads are only 1 kilowatt. We've only got 1 kilowatt of load here. Well, the difference will be going out to the grid. So we're spilling out to the grid 4 kilowatts of power, and it's renewable energy. And, you know, really, unless you're lucky enough to have a feed-in tariff that's higher than your purchase price for electricity, you don't want that to happen, particularly if you've got a battery inverter. You want to turn that around and store it in your battery. But how does the battery inverter know when to charge its battery? It needs that energy meter to communicate that energy flow. So it's got usually a cable, so that's a comms cable there, but you can do it wirelessly. So the comms cable will communicate with the battery inverter, indicate there's an opportunity to capture spilled renewable energy. That's the terminology we use, spilling energy. So it's going to then try and turn that around and stop it flowing the wrong way and allow that extra 4 kilowatts, so 1 kilowatt still going to the loads, but we've got 4 kilowatts now going to the battery. And so the energy meter is measuring 0 kilowatts of exchange at the point of connection to the grid. Looking at the Q&As over here, is AC coupled the same as grid tied? No. So coupling is how does the energy, let me just clear the screen. Second here. Coupling is how does the energy get from the solar array back to the inverter. Clear ink. Here we go. Whoops, didn't want to do that. So I'm just doing live drawing here, guys. So sorry about that. Yeah. So the coupling is how does the energy get from here to, where's my pen? From here to here. And the coupling is through an AC network. So it's AC there. So that's what AC coupling refers to. Thanks for that comment, Fatakas. Are wireless energy meters available and reliable? Cable may not be an easy arrangement. So I've recently been given some wireless RS485 devices. Thanks to one of my supporters, and that will allow the inverter to communicate via RS485. That was, by the way, that was Supply Partners. I just remembered their name. Sorry about that, Supply Partners. Thank you for sending it to me and for testing purposes. And it allows the communication between the energy meter to be converted to a wireless signal with a range of about 30 or 40 meters to the battery inverter. Now, is it reliable? Almost all AC coupled systems will use that information to choose when to charge, and if they have no information, they won't charge. So it is safe because if it stops working, your battery inverter system will just sit there doing nothing. So that's safe. It may not be ideal, but it is perfectly safe because cables are sometimes a problem. Now, I just see that we've got another question there. Hi, Frank. I just wondered, are there any points accrued with these seminars? I presume you're talking about the CCC CPD points. No, I didn't bother applying for any. Really, I'm just giving this as free training. I don't want to go through the whole CEC process to get points for it. It's up to you if you find this valuable. Russell, it's quite a long question. My question is, why is it that only qualified electrician can install and move into the licensed side of solar installs? Is this the law in Australia and New Zealand that because of the voltage levels, it is a licensing requirement? If you're working on an electrical system in the LV range, whether it's laying cables, connecting cables, building components in the switchboard, it's electrical work, and therefore it's covered under every state in Australia by an Act of Parliament. So it's just the law, I'm afraid. I know TV techs can work at some very high voltages. My background's actually electronics, so I've worked in the electronics world, but in New Zealand, but I can't work in LV systems because I'm not a licensed electrician. I'm a technician. So there you go. But you can always employ electricians. They're very good at their work. So
there was just on a tangent, there was a question about suggested insurance for installer designers, for example, professional indemnity.
So it's good business practice to have the appropriate insurance for your business, and I'd certainly recommend that you get public liability and, if required, professional indemnity. I hold both of those. Don't really want to necessarily promote particular insurers. There's plenty of them out there that offer those services. Now, can you see two slides or one, Rachel?
One slide.
Great. We're doing a good job here. If you wonder why I keep asking her, I don't always see what you see, so I'm just making sure this is all correct. Now, we looked at AC couple.
Sorry, will you show us some diagrams of multi-phase systems in this session, or is that for another day?
Well, sort of. Not in great detail. Really, any of these could be a multi-phase system. I just put 3 dashes on that blue line and it's suddenly a multi-phase system. If you think I'm being facetious, it's because multi-phase can be symbolized in a single line diagram just by doing 3 slashes onto a cable, indicating that it's 3-phase. So let me just contrast the AC coupled. I'll take you back to that slide just to remind you. That's AC coupling, right? So we're connecting via the AC network a battery inverter system to a solar inverter system, and it's an easy retrofit solution, whereas this is a DC coupled solution. Now this would be more typical of a new build where you want everything in the one package. You want the inverter to be have batteries connected to it and a PV array. So there's some advantages in doing this, but just as with the AC coupled system, it's important that the energy meter is upstream of all the loads. Otherwise, it can't see when to support those loads. Now, just to make that a little bit clearer, and I just wanted to illustrate this requirement is still a consideration, is that you have a means of communicating between your energy meter, so that's usually a comms cable, and the hybrid inverter. Now that's not a utility meter. That's often a small, 1, 2, 3, 4, even 6 pole dedicated energy meter that comes with the equipment. So it's not normally a separate purchase, though sometimes it is in larger commercial systems. And that energy meter goes in, hopefully, the main switchboard. Now, if you can't put it in a main switchboard, you only support the loads that are downstream of that meter. So it's pretty important when choosing a location for your hybrid system that you can get the energy meter that's associated with that upstream of all the loads you want to support. Because if it can't see the energy being consumed, therefore from the grid side, it's importing it from the grid. If it can't see that, then it won't export power from its battery system to support that load. So just to illustrate that scenario, here we go. So the customer turns on their heater. So they've got a 2.4 kilowatt load that comes on. Initially, we will see that energy coming from the grid. So we'll see 2.4 kilowatts coming from the grid. The communication with the hybrid inverter may take a few moments. So it's not instantaneous, and that's for reasons of flicker. It will ramp up to try and displace that grid power. So what it'll start to do is increase its output. So the energy will be coming from the battery and the solar if the sun's shining at the same time. And actually they merge together internally, so we'll just draw it like that. And so it'll try to meet that load. So it'll try to produce the same amount of export, and therefore it will reduce the exchange from the grid to zero. And that can take 10 to 30 seconds or so, but it will ramp up and match that exchange. So that meter is critical in that process. Rachel, we've got some more questions. I see there's one up there at the moment. At some stage, can you touch on EVs and V2G, V2G, vehicle to grid? It's actually a topic for another series, and I must admit, Rob, I'm not really an expert on EVs and V2Gs, so I'd have to do a little bit of research on that one. But it's certainly the future. If you ask me, if you buy an EV and it's got a battery in it, its chances are it'll be the biggest battery you ever own. It makes a lot of sense to be able to both charge it from renewable sources and to discharge it back into the home. The problem we have in New Zealand and Australia is we don't have a standard for vehicle to grid. Even though some state governments are kind of very excited by it and promoting it, we don't actually have a standard for it yet. It is on the roadmap, by the way, for Standards Australia. I'm actually on the committee that writes those standards. It's on our roadmap to produce a standard or a subset of an existing standard that will cover that in the future. But that could be some years away. So thanks for that one, Rob. So back to my diagram here. I'm just trying to make the point that it's all about understanding where the energy is coming from, and the energy meter is critical in that process. So, we've got another couple of questions. What happens when the grid drops out? Very good question, Paul. It depends is the answer. It depends very much on what type of system you have. So let's bring it back to, for instance, the first example, the AC coupled system. So this AC coupled system, if the grid were to fail, so we sever our connection with the grid, as I've drawn it, the solar inverter will island immediately within 2 seconds. It's a requirement. And the battery inverter, as I've drawn it, will also island because it's required to comply with 4777. So both of these will turn off. So this system, as I've drawn it, 4777 Part 2 is our grid protection standard. Those two ports on those inverters must disconnect from the grid within 2 seconds. So you might think, well, hang on, Glenn, what's the use of having a battery if when the grid fails, you have no power? Well, it's not all about having power when the grid is operational. Often it's about, or most of the time, it's about self-use of renewables. So there are systems out there that will only work when the grid's present and provide no backup, but when the grid is present, they're providing a way of storing surplus solar and allowing the customer to consume it at another time, at night time or when there is a deficit. So it's about self-consumption. But there are ways of adding backup to this design here, which I'll get onto. Wow, questions coming thick and fast now. So to clarify, George asks, so to clarify, hang on, let me just that question there. So George asked, to clarify, how does the inverter push the grid power away? Well, it's actually really Ohm's law. An inverter must increase its output voltage slightly higher than the source, or it becomes the source, and it will displace energy towards the loads. And it's an impedance circuit. If you really understand the electronics side of it, electrical theory behind it, the impedance of the grid will be high, the impedance of the load will be low. And so as the inverter increases its output voltage, but in perfect phase with the grid, of course, it will then flow towards the loads. It's a bit of magic, George. That's probably the best answer. Anonymous asks, does the energy meter fall under the inspection criteria? I haven't seen one yet across the ditch. Gee, I'll be surprised if you haven't seen one, because if you put in a hybrid system without an energy meter, it'll do nothing. It'll sit there, charge up on day one and do nothing. You probably are talking about pure grid-tied systems. An energy meter in that situation without a battery storage system is not required. It's sometimes an add-on option so the customer gets better monitoring of all their loads as well as the generation. Nura, can we have both AC and DC loads being fed at the same time? DC loads. So you're probably talking about an off-grid system there, I imagine, Nura. A DC load might be like DC lighting. Yes, you can do that. You can have DC loads directly connected to a battery. This is more of an off-grid configuration, though. So let me go back to my diagrams, and we were looking at a DC coupled system and talking about the pros and cons. One of the advantages of a DC coupled system is that it can charge the batteries even when the grid's not available. So over to that now. All right, so here we have a DC coupled system, but it's got a dedicated backup, or not dedicated, it's got a switched backup circuit. Now, what I've done, sorry, electrical engineers, that's not a proper symbol for a contactor. It's just me doing a 5-year-old's drawing, but represents a changeover switch that when the grid fails, that little box there, which is often called an ATS or automatic transfer switch, that little box automatically isolates the inverter from the grid side. So when the grid fails, it switches and isolates from the grid, which is a requirement from a safety perspective. And it then switches its internal mode, its port, we'll call it. So this port here, it will go from 4777 compliant port, which means that it will isolate within 2 seconds, but it changes it to a standalone port, or SA for short. And as a standalone port, it then will become a grid-forming inverter, which we talked about earlier. So that might take some 10 seconds or so. So this type of system is characterized by when there is a failure in grid power, the lights go out, and then they come back on again, because that inverter has to switch modes from a grid paralleling system to a standalone inverter, and it has to do it in isolation from the grid. So that is one way of providing backup when the inverter actually only has one AC port. Okay, so just looking at again here, thanks, some good questions here. Do residential sized inverters use reactance, Q or power factor to control the main voltage within the required range? So Richard, yes, it actually is in 4777 part 2, the design, the test standard for inverter systems, to be able to have that ability, and it describes what the ranges are of reactive power. We call it VAR volt mode. So VAR volt meaning VARs are reactive power, VAR volt mode, and that is being implemented now by many of the distribution companies as a requirement to connect an inverter system to the grid. The benefit of being able to have a reactive power component to the output of inverter is it doesn't increase grid voltage. So your inverter stays on. If the grid voltage starts to climb too high, your inverter starts to produce more reactive power and less active power. Now, if this is above your pay grade, just consider it as a way of inverters doing the right thing. They're not switching off. They're not causing the grid to go out of range, and they're still producing some useful contribution to the grid. They can also provide a little bit of power factor correction, but that's not very well controlled. It's kind of accidental. Veli asks, is there any issue with a circuit breaker rating specs in the grid fails and there is an earth fault when in backup mode? Veli, that's a little bit hard to explain without a circuit diagram. So look, I might have to just skip that question, but it's a very valid one. We do need to consider the fault paths under any MEN system. Fabio asks, should you take into account also the VAR response of the inverter when talking of export and inverter voltage phase, inverter injects VARs? Yes, so VARs, unless you're a commercial customer, generally aren't worth anything. So producing VARs allows the inverter to not make the grid push it out of range, doesn't push the voltage up, but you're not actually getting paid for that contribution. Oliver asks, can you please give a summary of some of the requirements for fireproofing? We're going to cover batteries in more detail later on, so sorry about that one. We'll leave that question at the moment, but we will talk about the requirements for battery systems and the protection against the spread of fire. Does the ATS shown on the battery with the backup diagram have a certification requirement in order to be safe? Also applies to the CT that would trigger operation of the ATS. Gee, you guys are really into the so that ATS is a piece of electrical equipment. It needs to be suitable for its application. So like a circuit breaker or any other equipment installed into an electrical system will have test standards associated with it. It may fall under a application by the utility that you need to have that tested. So when you're doing commercial systems and you may have some grid protection requirements, they may even specify what those products can be, or they may want to come and test them. So yes, there is definitely some safety considerations around that. And Dean asks, what is a good size inverter for a hybrid system for a standard house? Dean, it really depends what you want to do. I'm not being facetious here. It depends on the market you're into and what incentives there are around. An interesting fact, and all New Zealanders, please cover your ears at this point, is in Australia we get an incentive for solar panels, not for batteries, not for inverters. And that incentive will a financial boost to the amount of solar, a boost in the cost reduction by adding more solar. So actually incentivizes oversizing of your PV system to what you actually might need from a pure kilowatt hour per day basis. Something interesting that Renew, the organisation formerly known as the Alternative Technology Association here in Australia, did was do a survey of their membership to find out what size systems people had and what benefits they got. And the simple executive summary of that research was bigger is better. So ironically, a bigger system is often, it has a shorter payback, even if it produces more energy than you need. It's tied into the rebate system in Australia. Richard, so I've answered Richard's question. Mike, hi Glenn, with regarding to disconnecting from the grid when the grid power fails, can you run a battery as a UPS so that the equipment, i.e. computers, do not go off when the power fails? I feel like 10 seconds power outage might be too long. There is actually a separate standard for what's known as uninterruptible power systems, or UPS for short. That's AS 62040, and it covers the requirements for a dedicated backup system. Now, it's funny, every time I scratch my head, I just realize someone told me don't touch your face because we're we're not supposed to do that. So sorry about that. So, yep, you can actually have systems that don't have that break, but they fall under a different standard, so they're permanently on. You can't have a no break, completely no break with the grid unless you have a paralleling system that runs independently of the grid. The DC coupler, the charge, Chenyu asks, for DC coupler, the charge and inverter system is supplied by the DC battery or solar panels, or must you be supplied by one contractor? Many systems are built in stages and over time, and people often add components to it. So for instance, one contractor might install a hybrid inverter with solar only. Even though it's got a battery port, there's no battery connected to it. Adding a battery to that is possible at a later stage, and it's different electrical work. It may require inspection depending on what your jurisdiction is, and it may be done by a separate contractor. Paul asked, what do you mean by load center and the backup of a load center? Load center is just another term for a switchboard where loads are connected to. Okay, let me get back to my presentation. Thanks for that little burst of questions. It's really great to have this engagement from you all. So we've covered this one, AC coupled. We've covered a simple hybrid DC coupled system, but now we're looking at a different way of AC coupling. Now, this is why I started today's discussion, that the terminology AC coupling can be misleading because there are many ways to do it and they have different outcomes. Now, if you look at this diagram, you'll notice that there are a battery inverter which has two AC ports. It's got a grid port and it's got a load port. And so it's got two AC feeds going into that one inverter. And what's different about this battery inverter is it will accept power on its load port, the right-hand side of this diagram. And it's capable of charging its battery from that solar inverter system independently of the grid. That is, you know, a somewhat useful feature if you have a lot of blackouts, is to be able to independently charge from the grid. And it also is kind of special because not many battery inverters can do this, which is they may well have a backup circuit or a backup output, but it's not designed to accept power input on that backup circuit. So there are some systems that allow you to do this. Now I'm going to draw on top of this, so I'll just switch over to pad. Hang on. Stop sharing. Okay, so you should be seeing that same drawing now. You'll notice that I talk about grid-only load center. That's kind of optional, but you may choose that some circuits aren't critical to be backed up. For instance, maybe your hot water service, large resistive element. Maybe you've got a swimming pool pump, doesn't have to run all the time. So you may have some loads that when the grid fails, they automatically drop out. Whereas critical loads, we'll call these critical, you want these to be powered during grid outages. So this is your critical load center. Now, if the grid fails, in this configuration, using a special inverter, or there's many brands of them, but just pointing out that it's not a normal feature of every inverter, it can accept power flowing from the solar inverter and send it back into the battery on its backup port. So that's more typical of off-grid inverters, which have this feature, even though many off-grid inverters can be used on-grid as well. So this is AC coupling with a load port AC coupling as opposed to on the grid side. And it allows the system to charge batteries from the solar even when the grid's not available. So I'm just jumping over to look at questions now. So Fabio, thank you. Do you know if there are on the market some DC chargers suitable for managed lithium-ion batteries? So you've used a term there which we haven't covered yet, that a managed battery is one which has communication between its charging source and the battery management system itself, the BMS. And that management is about safety and performance. So to have a DC charger that will communicate using the proprietary protocols of that BMS is a bit of a special case. Yes, there are some. I'm not going to be sort of putting brands out there at this point, but there definitely are some. It's a question you would ask, for instance, if you're thinking of doing this and you have a favorite battery or a favorite charge controller, you might say, which batteries, managed batteries can you work with? But there are easier choices, Fabio, which is to use a self-managed battery. We haven't really gone into this in any detail, but superficially, I'll just answer this one as a self-managed battery, such as a lead-acid battery. It doesn't need a communication cable to it, but you can also get lithium-ion batteries that are self-managed. They don't have a communication cable. They manage safety internally. So there are ways of doing this which are quite simple. Good. Yes, Fabio, that Power Plus definitely make a self-managed battery. Thanks for that one. All right, so we'll go back to my presentation, and I'll just bring that back up again. We're getting towards the thin end of the webinar, so we've got about another 10 minutes, and I really want to push on with this content. I'm impressed by how many questions I get. It's really great, and I've been running a little bit behind my schedules that I promoted when I promoted this webinar series. So apologies for those who thought we'd be further down the track, but I guess I'm just responding to the wonderful amount of feedback through Q&A. So what we're looking at here is that AC coupled system that allows charging to occur via the battery's load port from the solar inverter. And I've put the pros and cons here just to summarize them. The pros are that the solar works without the grid. Now, this is kind of a small benefit if you have only intermittent grid outages, but if you've had outages that last days, it's very annoying to have a solar array on your roof and a battery inverter system, but it won't charge because it can't couple on the AC side without the grid being present. You also note there's no energy meter required in this diagram because all of the energy that we're interested in is passing through the battery inverter, and so its internal measurements are used to choose when to charge and discharge. The slight limitation of this design is that the internal contactor of that battery inverter will limit the maximum current you can draw from that switchboard or load center. But it's not a big deal. Many inverter systems allow you to have external contactors that you can control as well. And it does require, and this is proprietary generally, some way of controlling the solar inverters when the grid is not present. Now, what I mean there is if the grid fails and you are charging from a solar inverter via your battery inverter, your battery system, what happens when that battery's full? How does the solar inverter know stop pushing power towards the loads? Stop pushing power out. So that's where communication comes in, and it can be done with frequency, or it can be done with a data cable, but you need to tell that solar inverter, the battery inverter does, when to ramp back. Right. So DC coupled. Glad I got onto that before we finished. DC coupled system historically was the only way of charging a battery. DC coupling used to be extremely simple, and effectively connecting a solar panel straight to a battery was the way we used to do DC coupling. But these days we use charge controllers, because if you directly connect a solar panel to a battery, you're going to get very inefficient charging and possibly overcharging of that battery unless you manage it. But it does mean that you've got a dedicated way of charging the battery. You don't need anything else. You don't need the grid. You don't need AC sources to be around. It's just going to charge. The sun shines and you charge the battery. Many AC coupled systems are an all-in-one solution. So they can have solar connected and grid connected all in the one package, and so they will work independently of the grid and charge batteries. It doesn't add another inverter to your installation. Now, what I mean by that, IES limits, inverter energy systems, plural, limits are written into our grid standard 4777 Part 1, which is the installation standard for inverter systems. It says that the maximum inverter energy systems per single phase installation is 5 kVA, roughly 5 kilowatts. Now, if you've got a 5 kilowatt solar inverter and you want to add batteries, and you try to add an AC coupled battery, it's probably got its own 5 kilowatt inverter built in. So now you've got 10 kilowatts of inverter energy systems. Now, most utilities actually don't care, or they have low limits on this. And so, well, I shouldn't say don't care, they do care, but they have they don't enforce this 5 kVA very vigorously, because it's up to them to choose what those limits are. But we will see that limit drop down. So in parts of Australia, it's already at 5 kVA maximum per single phase installation. It's bigger for multi-phase. But if you've got a DC coupled system, you only got one inverter. So adding solar doesn't increase your IES capacity. You may not require a power meter if you're just directly supplying via your backup circuit the loads that you want to support from from solar. And it's often, DC coupled systems often do have a backup option. Now, for those who are not familiar with the Clean Energy Council in Australia, to access government rebates, we are required to comply with the CCC guidelines. They have in their guidelines a slightly perverse rule, which is the maximum PV size compared to the AC output of an inverter is 133%. So that means if you've got a 5 kilowatt inverter, you can't put in more than 6.6 kilowatts of solar on that inverter if you don't have batteries. And that's the real limit on oversizing. But anyway, DC coupled systems, because they've got a battery, aren't affected by this. So you can actually oversize a lot more. It is possible too with DC coupled systems to have a battery ready install. That means it works as a grid tie, grid connect inverter, even without batteries. And so the batteries can be added later. On the con side, generally DC couples are a little more complicated unless they're all in one package. They often have quite small backup ratings. When I say small, I'm talking like 2.3 kilowatts to about 5 kilowatts maximum. So they're designed for just essential loads, not running your whole house. And that last point's a bit of a joke. So we've got a question here. I'm working with Alpha 3-phase inverter, looking at putting in 3 2.9 kilowatt batteries, one on each phase. Great. I'm not sure if that's a question. It's a comment. So there is a requirement in our grid protection standard to, once you get to 5 kilowatts on a multi-phase system, you need to have a balance across those phases. So you can't put more than 5 kVA per phase. So you need to have balance if you go over 5 kVA per phase. I guess that's kind of what Ella's pointing to. Oops. I pressed too many buttons then. There we go. DC coupled. So we've got 5 minutes to go. So just get ready if you've got any last questions. I'm getting close to the wrap up. So just to summarize, DC coupled systems are simple. They may charge batteries without the grid. They require an energy meter for self-consumption of solar where the load center is upstream of the hybrid inverter. And in this diagram, only the loads are supported when the grid is present, no backup. However, it is possible with some of those hybrid inverters using an automatic transfer switch to add a backup capability. And there are some which have a dedicated backup circuit output as well, such as this. So this would be where the hybrid inverter has 2 AC ports. One says grid, one says backup. And some of these switch very, very quickly too. It's still a break, but it's often 10 milliseconds or so. So if you're looking at a virtual no-break system, some will do this. It's a very quick switch. So Robert asked, how do you rate short circuit current and time for cable ratings on DC systems? Probably beyond the scope of this presentation, Robert, but I would be going to the manufacturer in terms of the current time series for their cable and therefore the protection that needs to match that. Shunyu asks, can a solar cell directly charge the battery? Are you planning on coming across to New Zealand to deliver any courses? Actually, across to New Zealand a lot. So that was the Haywoods. About 4 or 5 times a year, I go to New Zealand to run training. At the moment, mostly through Ideal Electrical. They bring me over and we run courses at their facilities around New Zealand. So yeah, thanks to Ideal for that. But unfortunately, due to the lockdown, my next 2 courses, which were about to happen in New Zealand, had to be postponed. All right, so just winding up this presentation. That the DC coupled systems with a switched backup, it does provide backup power, but the cons are you will have a loss of power for up to 10 seconds or so, or maybe even longer depending on the ATS. And you may have to provide the external contactor, or it may be built into the device itself. And if it's an external contactor, it will be more difficult. That DC coupled system with a dedicated backup. Now, here's another one. You don't actually have to choose one or the other. You can have AC coupled and DC coupled. So here we've got an existing solar inverter system installed in installation, the bottom inverter there, and the customer wants to add storage and they want to add more solar. So this is where they've added a hybrid inverter. And so they've effectively got both DC coupled and AC coupled systems in the same installation. Pros and cons of that is that the hybrid inverter can charge the battery from both sources because it's got an energy meter that can see energy flowing from the solar inverter. It does, on a con side, mean that you've got 2 inverters now, so you're increasing your IES capacity, and we do require that upstream energy meter. And as this diagram happens to be drawn, there is no backup circuit, but that can be solved. Okay, so we've come to the end of today's webinar. For those who have joined and haven't seen my previous ones, these are being recorded. I do a rough edit to get all the glitches and face touching out for Taka, so you won't see that. And I'll upload it to my YouTube channel. So you can view these probably later tonight or tomorrow at, just go to YouTube and type in Smart Energy Lab and you'll find these webinars. So thanks very much, everyone, for attending, and I'll be back tomorrow at the same time, same place. I've still got another 10 of these to do. So thanks a lot, everyone. Bye. Thanks for attending today's session. Tomorrow, we're going to be looking at off-grid systems. and understanding the system configuration options from single line diagrams through to understanding the difference between generation and load and the importance of combining a design that considers both. Looking forward to it. See you tomorrow.